Welcome back to our series of geotechnical engineering. Today our topic will be principle of effective stress, and then we will cover capillarity topic. So let's start with principle of effective stress. So the principle of effective stress is mainly given by Terzaghi. This concept directly connected to shear strength of the soil, compressibility of the soil, and lateral earth pressure of soil. So principle of effective stress governs these three areas related to the soil. Now we know in any soil mass there are many particles. Now if this is my soil mass and there are n number of particles, and on each particle there will be a normal stress. Now summation of those all normal stress is represented by sigma n, and for the ease of calculation I take the cross section of my specimen. Now this stress will be called the total stress, which is denoted by sigma, that is summation of all the normal stresses upon area of the specimen. This stress is measured by device called pressure cell. Now suppose this is my specimen. There are layers of soil. The topmost layer is of depth h1, and that layer is dry and having a unit weight of gamma 1. Then below it there is second layer of depth h2, and it is in saturated condition and it has a unit weight of gamma 2, and beneath this I have a plain bed. Now I apply a surcharge of q magnitude over this setup. So now if I have to find the total stress for this specimen, now from top to bottom I have to find all the forces, that is all the forces, then I will divide it by the area perpendicular to the applied force. So let's start from the top. So there is a surcharge stress q applied over area A. So this is the sum of this stress over this area. Now if we come below it, then there is the first layer of dry soil. So in this layer the unit weight is gamma 1 into the depth is h1, and the area perpendicular to the applied force there is A. So the product of this will be gamma 1 into h1 into A. This will be the force due to this soil layer. Then below it there is another layer of soil, that is saturated soil layer, having unit weight of gamma 2. So gamma 2 and having depth h2, and the area is A. So this is the force due to this layer. Now summation of all the forces divided by the area will give us the stress, the total stress. So we will get sigma equal to q plus gamma 1 h1 plus gamma 2 h2. So this will be the total stress. Now also if in the saturated layer I inserted a piezometer, so there will be the reading of the water in the piezometer. Suppose at up to this much height the water has risen. So here in the saturated soil layer I will insert a piezometer. The water will rise up to a height which will be equal to the height of the saturated layer. Now in this the pore pressure will be measured as U equal to depth of the soil layer h2 into gamma w, unit weight of water. So this will be the pore pressure. Now the pore pressure is also called the neutral pressure, and it is measured by piezometer or transducer. Now as we know, total stress is equal to pore water stress plus effective stress. Putting the values in this equation, it will looks like sigma is equal to U plus sigma bar. Sigma bar means, or sigma dash, these two representations used to represent the effective stress. So from this equation we can find out that sigma bar, like effective stress, is equal to total stress minus pore water pressure, because this effective stress is grain to grain pressure, not physical. It is not physical. Effective stress is not physical, so it can't be measured directly. Also effective stress if increases, then packing will increase, the void ratio will decrease, and the shear strength of soil will increase. So we can't find the effective stress directly by measuring by some device. So we use this relationship between the total stress, pore pressure, and the effective stress to find out the effective stress. Now this equation only for normal stresses. When the stresses are normal, then only this relationship held true, otherwise it will fail. So it is not for shear stresses, it is only for the normal stresses. So this is the concept of the effective stresses. Now capillarity in soil. So suppose there is a landmass like this. Now this is a depression. Now rain is happening. Some water will obviously get absorbed into the soil, will finally reach to the groundwater table below the saturated section of the soil. Now some water will also be run off and get stored into the depressions, and this depression or river will also get the water from the seepage from the groundwater. Now this is we know normally. Now there are sections or zones in the ground which we can classify as zone 1, zone 2 and zone 3. Now what are these zones? So zone 1 is the submerged zone of the earth or soil. In this zone is always submerged below the groundwater table. Above it there is a zone which is called capillary zone, and above it there is a zone 3 which is called aeration zone. So in the capillary zone, like above the groundwater table, there is some, like this is the groundwater table, then there is some limit of the distance up to which the water can rise in fine voids of soil due to the surface tension force, or we can say the capillary force. So the depth of the soil mass up to which this capillary water can rise, this zone of the ground is called zone 2, which is capillary zone. Above this capillary zone, the soil mass has section in which the voids are completely filled by air and the water is very less in the voids. So that section is called zone 3, that is aeration zone. So there are 3 zones on basis of the presence of the water in voids. Zone 1, that is submerged zone, means the voids is always filled with the water. And there is capillary zone, in which water can rise up to a certain height due to the surface tension. Then there is zone 3, in which the voids are filled with air only, there is no water or very less water. So the upper surface of the groundwater zone of full saturation. So the upper surface of zone 1, that is submerged zone, is at full saturation, and this upper surface is called the water table. Now water table is phreatic surface. So water table is also called what? Phreatic surface. Now water table is at atmospheric pressure. So we have to remember that water table is at atmospheric pressure. Water table has pore pressure equal to 0. So at the water table, the pore pressure will always be 0. We have to remember these points. Now zone 1. Zone 1 is below groundwater table. Pore pressure is positive, that is hydrostatic. Now zone 2 is above groundwater table. Water rises to some height by capillarity. Now zone 3, above capillarity zone, soil particles has hygroscopic water around itself, which is retained against gravity by action of capillarity. This zone is called aeration zone. Now let's study the capillary rise. So suppose there is a beaker in which I have a fluid, suppose water. Now I have a fine tube which are inserted like this, that this tube just touches the surface, or maybe just few or maybe just dipped in the surface for few depth. Now what happens? We know that surface tension is force per unit length. So this means that the relation between the surface tension and the length of the surface is inverse. So if the length will decrease, the surface tension will increase. So suppose if there was a beaker in which I have fluid, in this state the length for the fluid is L. Now if I inserted a tube in this, a fine tube, thin tube, then what happens? For the liquid inside this tube, the length is decrease. So the length will decrease, so the surface tension for this much water which is inside this tube will increase. So when the surface tension will increase, the water inside this tube will rise up to some height. So this height up to which the water rises in fine tubes is called capillary rise. So let's find out. its value numerically. So we have here the setup. Now suppose the water rises up to this height. Now in the fine tube, water suppose rises up to this height. So the top surface of the fluid inside the tube will not make a horizontal surface. It will make either a meniscus like this or a meniscus like this. Like in case of water, you will find this type of meniscus, and in case of mercury, you will find this kind of meniscus. So these are called meniscus. Now in our tube, the water rises up to a height hc from the free surface of the fluid in the surrounding. So the weight of this much section of water which is raised up to some height due to the surface tension. So this weight of this water section will be equal to the surface tension force due to which is it raised. So surface tension force will be the T component. So this is T. Now this T will be resolved into two components. One is sine component and this will be the cos component. Now the cos component of this is rising it upwards. So we will find it like T cos alpha into the surface tension is due to the perimeter of the tube. So surface tension force into the perimeter pi d. This will be equal to the weight of the column of the water inside this tube. So that will be pi by 4 into d square into hc, that is the volume of the water column, into gamma w, unit weight of water. Now these two quantities will be equal, so we will get hc is equal to 4t cos alpha upon gamma w into d. So we can see like capillary rise, the height up to which water will rise, has inverse relation with dia of the tube. So that if the dia of tube decreases, the height up to which liquid rise will increase. Also we can see from this relation that the capillary rise is directly proportional to the alpha, the angle made by the meniscus with the tube. This angle is called alpha. This angle is alpha made by the meniscus with the tube. Now for water, there are two special cases. At 4 degrees centigrade, height of the capillary rise is given directly by hc equal to 0.3084 divided by d. This will give you the capillary rise in centimeter. Also at 20 degrees centigrade, the capillary rise can be found by 0.2975 divided by d. So again you will get the capillary rise in centimeter. Now Terzaghi and Peck has given their formula for the capillary rise in the case of soil, and it was hc, capillary rise, is equal to c, that is a constant. Its value is somewhere 0.1 up to 0.5 centimeter square, and c divided by e, like that is void ratio, into d10, and this formula gives you the capillary rise into centimeter unit. Here you will have to put the value of d10 into centimeter. So this is the Terzaghi-Peck formula. Also capillary pressure. Now capillary water exerts tensile force on soil, results in negative pressure. Now the capillary rise, if there are soil particles in the way of the liquid and the water is rising due to capillarity, it will exert a tensile force on the soil particles. So and this will act as a negative pressure of water, and it is called capillary pressure. Pour water under compression. Now if there are pores, in these pores there is water, so if we apply stress, this stress will be first taken by this pore water. So pour water under compression, when you compress the soil mass, the value will be positive for the pore water pressure, and if the soil mass is under tension, then the pore pressure value will be negative. So in capillary zone, the effective stress is total stress minus, in capillary zone it will be the negative pore pressure, so the effective stress will increase. So in case of capillarity, due to capillarity the effective stress increases, hence shear strength is also increases to some extent. That is, capillarity increases effective stress in soil, hence the shear strength will also increase. So that's all for this lecture. Here we have covered the principle of effective stress and capillarity in soils. Thank you.